After studying this module, you shall be able to know about metal nitrosyl ligands and their bonding modes, and also about commonly known nitrosyl metal complexes. We will also learn about various bonding modes of nitrosyl ligand in metal complexes. We will also learn about various methods of synthesis of metal nitrosyl complexes. Nitric oxide is a colorless monomeric paramagnetic gas with a low melting point. It is thermodynamically unstable and decomposes into its elements at elevated temperatures. Nitric oxide has one more electron than carbon monoxide and often acts as a 3-electron donor ligand. Nitric oxide display a wide variety of coordination geometries such as linear, bent, doubly bridged, triply bridging and quadruply bridging, where it is bridging 4 metal ions. In the past 20 years, metal nitrosyl complexes have gained considerable attention because of their important role of nitric oxide as signaling molecule in various biological systems. Luis Ignarro received the Nobel Prize in Physiology and Medicine in 1998 for his discovery of the signaling properties of nitric oxide. For such purposes, the iron dithiocarbamates are utilized as model compounds for nitric oxide spin trapping. The first nitrosyl complex was discovered in 1790 by J. Priestley, having the formula iron penta-aqua nitrosyl 2+. This complex is also formed in the quantitative test for nitrate with ferrous sulfate and sulfuric acid, which is also called the brown ring test. Nitric oxide is the simplest thermally stable odd electron molecule which can readily react with transition metal complexes to give a number of nitrosyl complexes. Few features examples of nitrosyl complexes are the brown ring complex, iron penta-aqua nitrosyl 2+, the sodium nitroprusside, disodium pentacyano iron nitrosyl to water, and the Rosin's salt, etc. The nitroprusside ion pentacyano iron nitrosyl 2- has been used as a vasodilator for the treatment of high blood pressure. This complex is able to release its nitrosyl ligand where nitrosyl acts as a vasodilator and hence show therapeutic effects. Most of the nitrosyl complexes are highly colored, such as deep reds, browns, purples and even black. Apart from the increasing interest in the structure and bonding of these compounds, there is an upsurge interest in their utilization as homogeneous catalysts in a variety of chemical reactions. Now we will come to know about bonding modes of nitrosyl ligand in metal complexes like carbonyl CO. Nitrosyl NO is a sigma donor and pi acceptor ligand. It can show both terminal as well as bridging bonding modes on its metal complexes. Nitrosyl as ligand behaves differently. Unlike carbonyl, nitrosyl can show two different types of bonding modes. in its complexes containing the terminal nitrosyl ligands. Nitrosyl can coordinate to the metal ion in a linear fashion as well as in the bent arrangement. The nitrosyl plus being isoelectronic with carbonyl and binds to the metal in linear fashion, whereas the bent geometry of nitrosyl is considered to arise formally from the nitrosyl minus species. The bent geometry directs towards sp2 hybridization on the nitrogen, although the use of labels nitrosyl plus, nitrosyl or nitrosyl minus does not provide an account of the ionic or covalent character in the coordinated ligand. These are used only for electron counting purposes. Hence, the nitrosyl ligand acts as a 1 electron or a 3 electron donor species. The nitrosyl cation NO plus can use its lone pair on the nitrogen atom to form a bond to the metal atom like its isoelectronic counterparts such as carbonyl CO and cyanide Cn minus. As carbonyl ligands, various degrees of pi back bonding are observed. NO plus is a stronger pi acceptor than CO. In the linear coordination mode, the bond angle between metal, nitrogen and oxygen is generally in the range of 165 to 180 degrees, whereas in the bent nitrosyl complexes, the MNO bond angle is generally in the range of 109 to 140 degrees. Increasing the strength of the pi back bond strengthens the Mn bond and weakens the NO bond. In extreme cases, both bonds can be characterized as double bonds, such as in the second structure. In cases in which the MNO angle is close to 180 degrees, the Mn bond is usually relatively short. If the back bonding effect is weak, the angle decreases significantly, as much as up to less than or nearly equal to 120 degrees. Infrared spectroscopy and EPR spectroscopy can be used to distinguish between the different bonding modes of nitrosyls, such as linear MNO groups, where nitrosyl contains a triple bond, absorbs IR radiations in the region of 1650 to 1900 centimeter inverse, such as in the case of pentacyano-nitrosyl ferrate, whereas the bent nitrosyl groups, where NO contains a double bond, absorbs in the range of 1525 to 1690 centimeter inverse. Classification of metal nitrosyl complexes. Previous section has described the most common bonding modes of nitrosyl as ligand in their metal complexes. However, a large variety of other bonding modes have also been observed. Nitrosyl, as we know, is a stronger pi acceptor ligand than carbonyl, and hence it forms stronger bonds with metals. This lowers the bond order in the nitrosyl ligand, and very small changes in coordination environment around the metal ion may result in substantial change in the bonding character of the nitrosyl ligand with the metal ion. This generates a possibility to undergo various types of bonding modes. Hence, apart from commonly found linear and bent structures of nitrosyl, there are bridging modes where the nitrosyl is bridging with two or more metal ions, such as linear, bent, two-fold bridging and three-fold bridging. In two-fold bridging, the nitrosyl nitrogen is bonded with two metal ions, whereas in three-fold bridging, the nitrogen is bonded with bridging with free metal ions. There are other modes such as diheptonitrosyl, triheptonitrosyl, linear isonitrosyl, and isonitrosyl bridges are also found. Sodium nitroprusside is believed to contain isonitrosyl bridges. In mononitrosyl complexes, the nitrosyl ligand display linear and band arrangements which can be easily distinguished using infrared spectroscopy. The MNO group in the linear arrangement absorb in the range of 1650 to 1900 centimeter inverse, whereas the bent nitrosyl display absorption in the range of 1525 to 1690 centimeter inverse. Because of different bond orders in the nitrosyl leads to different vibrational frequencies. Synthetic routes to metal nitrosyl complexes. The nitrosyl cation is isoelectronic with carbonyl, and the coordination chemistry of nitrosyl is often compared with carbonyl. Generally, metal carbonyls are frequently prepared by reaction involving carbon monoxide gas at high pressure and temperature, whereas the metal nitrosyls are not obtained by these routes owing to the thermodynamic instability and decomposition and disproportionation of nitrosyl gas at high temperatures. So, there are certain typical methods of synthesis of methyl nitrosyl which will be discussed. First, addition of nitrosyl to coordinatively unsaturated complexes. For example, in this case, the dichloro-diaqua cobalt complex, when reacts with nitrosyl, the nitrosyl adds to carbonyl and gives a higher coordination number complex. Whereas in the second example, the dioxophosphine dihalide cobalt complex reacts with two molecules of nitrosyl, giving a complex of higher coordination number. Second, we can also obtain metal nitrosyl complexes by substitution of other ligands. Since nitrosyl cation is isoelectronic to carbonyl, two molecules of neutral nitrosyl can replace three molecules of carbonyl. Likewise, one nitrosyl can replace two carbonyl molecules with simultaneous formation of a metal-metal bond, or one nitrosyl can replace one carbon monoxide and a halogen together. In the first example, we see the tricarbonyl nitrosyl cobalt ligand reacts with two nitrosyl molecules to give a trinitrosyl cobalt and three carbonyl molecules as side product. So, in this reaction, two nitrosyl molecules are displacing three carbonyl ligands to form the desired nitrosyl product. Whereas, in the second example, where pentacarbonyl iron reacts with two nitrosyl molecules to give a dicarbonyl dinitrosyl ferrate by replacing three carbon monoxide molecules. In the last example, the penta-aqua iodo manganese complex reacts with three molecules of nitrosyl to give a trinitrosyl carbon monoxide manganese complex, and 4 carbon monoxide and 1 iodine remains as side products. The third method involves reductive nitrosylation methods, where the reacting metal is getting reduced. The metals that shows these type of reactions are molybdenum, technetium, rhenium, ruthenium, osmium, iridium, and platinum. For example, when cobalt chloride reacts with 3 nitrosyl molecules in the presence of boron and alcohol, the desired product is obtained where the cobalt is found to be reduced. In this reaction, the boron acts as a proton acceptor like alkoxides and amines. The fourth method involves the addition or substitution of a nitrosyl cation. The nitrosyl cations can be obtained from various reagent sources such as nitrosyl tetrafluoroborate, nitrosyl hexafluorophosphate in methanol or acetonitrile. For example, The tetraacetonitrile rhodium complex can react with nitrosyl cation to form the product. In similar complexes such as tetracarbonyl diphosphochromium can react with two molecules of nitrosyl in the presence of acetonitrile to give the desired product, where the 4 carbonyl molecules has been replaced as well as the diphosphate molecule has also been replaced. The fifth method involves the oxidative addition of halide nitrosyls. These reactions occur with either coordinatively unsaturated or saturated metal complexes. For example, in the tetrakis triphenyl phosphate nickellate, the chloronitrosyl reacts and gives the product as chloronitrosyl bis triphenyl phosphine nickellate, where 2 triphenyl phosphine molecules has been displaced. The sixth method involves the reaction of metal hydride complexes with N-nitrosyamides such as N-methyl and nitrosourea. For example, in the pentacarbonyl hydrido manganese complex, which can react with N-nitrosamide to give a tetracarbonyl nitrosyl manganese complex, and where one of the carbonyl has been replaced. The seventh method involves the transfer of coordinated nitrosyl from various metal complexes such as dimethyl glyxosate complexes. For example, the dimethyl glyxosate nitrosyl cobalt complex can react with another complex to replace nitrosyl or to displace nitrosyl from the cobalt complex to the other metal complex. The eighth method involves the use of ammonium hydroxide in basic solutions. The use of ammonium hydroxide in basic solutions can generate nitrosyl anion by the following reaction, where 2 ammonium hydroxides can give ammonia plus water plus 2 plus the nitrosyl anion. The nitrosyl anion thus generated can displace anionic ligands such as cyanide or halides in their metal complexes. For example, the tetracyanonickelate 2- complex can react with 2 molecules of ammonium hydroxide in methanol to give a tricyanonitrosyl nickelate 2- complex with the release of ammonia, water molecule and methyl cyanide. The ninth method involves using of acidic nitrites. For example, sodium or potassium nitrates produce nitrosyl cation under acidic condition by the given reaction, where nitrate ion give rise to nitrosyl cation. This nitrosyl cation can react with various metal carbonyl salts to displace carbonyl ligands. For example, in the given reaction, potassium nitrates acts as a source of nitrosyl ligand to give the desired product, whereas in the second reaction, the sodium nitrate is the source of nitrosyl cation ligand. The second method, where the alkyl nitrites can also be used for these reactions in protic solvents to produce alcohols. The alkyl nitrites in acidic conditions generates nitrosyl cation and alcohol. This nitrosyl can then react with various metal ions to give nitrosyl metal complexes. Generally, alternatively, in aprotic solvents, the reaction also goes without any acid. For example, in this given reaction, the alkyl nitrite is acting as a source of nitrosyl, which is displacing 2 carbon monoxides to give the final product. In the second method, the alkyl nitrites can also be applied for these reactions in protic solvents to produce nitrosyl cation and alcohol. This nitrosyl cation can then react with various metal ions to give rise to nitrosyl metal complexes. These reactions can also undergo in aprotic solvents, where the alkyl nitrite acts as a source of nitrosyl ligand to give rise to the desired product. The 10th method involves the use of concentrated nitric acid. Concentrated nitric acid, 2 molecules of concentrated nitric acid can react to give rise to nitrosyl cation and nitrite anion. Some of these reactions results in the oxidative addition of nitrosyl to coordinatively unsaturated metal centers, whereas in others ligand displacement by nitrosyl cation occurs. This is an easy route to synthesize nitroprusside such as nitrosyl pentacyanoferrate 2. For example, in the hexacyanoferrate 4- anion on reaction with nitric acid generates pentacyano-nitrosyl ferrate 2- anion. The 11th method involves the oxide ion abstraction from coordinated nitrogen dioxide from the various metal complexes under acidic conditions. For example, the pentacyano nitrogen dioxide ferrate 4- in acidic conditions give rise to pentacyano nitrosyl ferrate 2- with the release of a water molecule. In the 12th example, we will see the oxygen atom abstraction from the potassium nitrate. For example, the pentacarbonyl ferrate can react with potassium nitrate to result in a nitrosyl complex with the release of one of the carbonyl monoxide molecule and oxidation of one of the carbonyl monoxide molecule to give CO2. The 13th method involves transformations using pre-existing nitrosyl complexes. For example, the other ligands can also displace existing ligands in metal complexes to give rise to new metal complexes. This can also be done in the presence of light as well as other stronger ligands. The nitrosyl ligand is a sigma donor and pi acceptor ligand. This can serve as a terminal or bridging ligand. The nitrosyl cation is a stronger pi acceptor than carbonyl. The nitrosyl cation can use its lone pair on the nitrogen atom to form a bond to the metal atom like its isoelectronic counterpart, the carbonyl and cyanide. Nitrosyl has two common coordination modes called linear like carbonyl and bent. We can also utilize infrared spectroscopy and EPR spectroscopy to distinguish between the two bonding modes in these complexes. The metal carbonyls are frequently prepared by using reactions between metal and carbon monoxide gas at high pressure and temperature, whereas the metal nitrosyl complexes are not obtained by these routes owing to the thermodynamic instability and decomposition and disproportionation of nitrosyl at high temperatures. Metal nitrosyls can be synthesized by various methods such as addition of nitrosyl to coordinatively unsaturated compounds or substitution of various ligands, which is called replacement method. Nitrosyl complex can also be synthesized by reductive nitrosylation methods and also by addition of or substitution of a nitrosyl cation. The oxidative addition of halonitrosyl compound can also lead to nitrosyl metal complexes. The oxidative methods are also involved where a halonitrosyl can be utilized. We can also do reactions of metal hydride complexes with N-nitrosamide such as N-methyl nitrosourea, which acts as a source of nitrosyl in situ. We can also utilize methods such as transfer of coordinated nitrosyl, especially from dimethyl glucosamate complexes, which can readily donate nitrosyl to give to other metal complexes to result in metal nitrosyl complexes. We can also generate nitrosyl from ammonium hydroxide in basic solutions, which can react with various metal ions. We can also use acidified metal nitrides such as alkyl nitrides or potassium nitrates and sodium nitrate. You can also use these reactions, or we can also do this reaction in concentrated nitric acid. Concentrated nitric acid also give rise to nitrosyl cation. Various complexes, when they react in nitric acid, results in nitrosyl metal complexes. We can also use methods of oxide ion abstraction from the coordinated nitrogen dioxide under acidic condition. Various metal complexes where nitrogen dioxide is one of the coordinated ligand can result in nitrosyl metal complexes under acidic conditions. We can also perform transformations using pre-existing nitrosyl complexes where other ligands can displace the existing ligand to generate new nitrosyl complexes in the presence of light as well as heat.